Hello, welcome to Dr. Taylor's Pedagogical Notes. We're going to take a look at estimating a square root of a whole number. Okay? So in this one, we're going to look at multiple strategies, again, concrete to abstract, etc. Since we're dealing with numbers, like in this case 28, we're going to use colored squares because 28 is a bunch of ones added together 28 times, right? And we can use different colors, doesn't really matter. There's an advantage to having two colors, and maybe three if you could, but you could do them all with one color as long as you're careful and you pay attention to what you're doing. It works. So let's just look at two different colored squares. So I'm going to look at two, all right? And what I'm going to do is I'm going to try to imagine it. If I had 28 squares on my table, make the squariest square I could, the biggest square I could make out of that. Now, obviously, if I don't have just the right number, I'm not going to make a perfect square. I'm going to have extras or whatever. And we're going to show what to do with that in this procedure. So I'm looking at what size squares I can make and that connection between a numeral that's a perfect square and what does it mean to be a perfect square. What is a square number? Where a square number is a number of squares that I could put together to build a square. Okay? That's why it's called a square number. Right? Numbers are for things. In this case, we're taking square things, and when we put them together, it makes square shapes. And when it makes square shapes, that's a perfect square. Okay? So let's take a look at this. All right. And so I'm going to have you look at a few arrangements and try to make the squariest square you can make out of that 28 shapes. And the timer would click on, and it would be 5 minutes, and then you would come up with your ideas. I'm going to not click it on. You can press pause now. And here you are. You're back. And you've done what you could do. And what did you do? You could have laid them out all one way, right? Now, I might not even have told you to make the squariest square, but how could you? I could have laid out 28 squares horizontally. I could have put them in any old way, right? Like a crossword puzzle or some stuff, right? I could put them in a giant rectangle, right? And that may not be the best way, but it might not be the worst way either. Point is, there's a lot of ways I can make them. But if I'm trying to make the best, biggest square I can make out of 28, what happens is I can get all of those in a square pretty good, but I got these three left over, and now you see what the advantage of two colors could be. So what is the square? What's the squariest square? What's the square? How many squares are in the square piece? That's what I would like you to look at. Okay? So when we look at this and we see how many squares are in the square piece, we see it took 25 squares to make that red area. But we had 28 squares, and so the leftover three, I could have stuck them here, there, over there, up there. It doesn't matter. I just stuck them somewhere to have them there. Okay? So now that I've done that, I can see that I have a square and some. Okay? So as I look at these numbers, 1 and 4 and 15, right, different ones, right? Maybe there was something between 4 and 15, hint, hint, hint. Right? When I look at these different numbers, I wonder, what the next biggest square would be if the 25 is the one I could make. So what I'm going to do is I'm going to take a third color, I'm going to take the green color, and I'm going to finish building the next biggest square. To build the next biggest square, I'm going to have to not just have these 5 by 5s, right? But I'm going to have to use those three and some more to finish. Well, if I just put 2 there, that's not going to make a square, it's going to make a rectangle, right? So what I'm going to do then is I'm going to put a row and a column, right? Because if I have a square and I only add a row or I only add a column, I won't have a square anymore. So to have a square, to stay a square, I've got to add a row and a column, or I can imagine an L going around it, right? So when I look at this now, it's clearly 5 plus 1 by 5 plus 1, right? What would that be? That would be 6 by 6, or you start to get the sense of what a square number is called a square number. So what was the number I had? 28, and I used 25 with 3 left over, right? So my square root of 28 is close to 5, right? Because it's 5 times 5, but it's a little more. How much more than 5? Well, that's where our remainders come in to make it so easy. We have 3, right? And so if I take those 3 and then I add up 3 and 4, 5, 6, 7. So what I have is 5 whole parts and 3 out of what? 3 out of 11 fractional parts. Okay? So if you took your calculator and you hit the square root of 28, you would get a number 5 point something. If you took your calculator and you hit 3 divided by 11 equals, and then you added 5 to it, you'd have a number 5 point something. And you would find those numbers extraordinarily close together. This is a great way to quickly assess what the square root of a number is, and a pretty good approximation. If you're doing an ACT test, it's that quick. 3/10 is 0.3, right? So it's close to 5.3, right? 3/11 is a little bit less than 0.3, right? Because the bigger this gets, the smaller I have. If I get 3 out of 10 billion pieces of pizza, I don't have much pizza if I got 3 out of 11, right? Okay. So 3 divided by 11, add that to 5, and you would do that. And so you get 5.272727. If I did the square root of 20, I get 5.29. So you can see that that's just 2/100ths off. Now, if I'm doing something super duper accurate, 2/100ths matters. But you know, if I'm cutting wood, 2/100ths, I'm not going to see 2/100ths. Or I'm not going to feel it. It's not going to matter. So 2/100ths is a pretty good accuracy. I'm within 2%. If you think about 2/100ths, I'm within 2% accuracy. And that's maybe not the perfect way to do it. If you did it, you know, through formulaic procedure, percent error, it would be different. But it's a ballpark estimation way. Hey, I'm within 2/100ths of the right answer, so I'm going to say I'm accurate within around 2%. 2% is great. If I got 98% in every test I ever took, I'd be happy, right? So it's okay. All right, well, let's take a look at this. Pretty good estimate, right? Let's take a look graphically. I draw it, right? So I didn't do a lot with it. I just didn't draw it again, but you would draw it, and that's what you would do. Now, number lines symbolically, 2 times 3, 4 times 4. You see what I'm doing? I'm counting up. But now I'm not counting up 2, 4, 6, 8. I'm saying, well, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. I keep going till it's pretty close. I do the next one. Oh, it's too big. So now I know, since 28 lives between 25 and 36, right? I can't do 36. I have to go back down, and that's 5. Now the difference is I have the 5 part, right? But I want to know what's the rest of it. So there's the 25 and the 36. Oh, remember when I said you don't have to always start your number lines at 0? Here's an opportunity when it wouldn't be very advantageous to do that. But if I'm counting from 25 towards the 36, which was the other perfect square, and I had how many square numbers? 28. So I'm going to have to count how many spaces beyond 25. Counting up, 26, 27, 28. So I'm going to jump 3 spaces. So now that's where it really lives. The perfect square and the perfect square between 5 and 6. It's going to be 5 point something. Well, that's 1, 2, 3 spaces out of how many spaces? Okay, 3 plus 8 is 11, right? If I'd have counted below here and not up there, I'd have counted 3 and 11, and that might have been a nicer way to look at it graphically. So that's 5 and 3 11ths. Again, 5 and the remainder, 3 11ths. 3 is how many jumps I had. 11 is how many it took me to get from 25 to 36. Okay. There's all kinds of patterns for perfect squares, from 1 to 4 to 9 to 16 to 25 to 36. See if you can discover the patterns between those numbers. What's happening? What's the difference? Is it common? Is there a pattern of difference? Look at them. Explore. Play with it. That's how it sticks in your head. Okay? All right. The abstract, without exceeding 28, I'm thinking 25. And I know, 6 times 6, so it's what's called interpolation. We all used to have to do it. Now you hardly do it at all because your machines do it for you, your calculators. Tables for trig tables and log tables and stuff like that are in there. The interpolation happens automatically. We used to have to do it ourselves, when the dinosaurs roamed the earth. So I've got 5, and I've got 3 to go, right? So that's 28 minus 25 is 3. 36, the next biggest square. 36 minus 25 is 11. And look at that. There's your fraction right there. What I have minus the stuff before it, the biggest square minus the square that I found, and that literally builds the fraction 3/11 that I would add to the whole value 5. All right? So I hope that you found this interesting and insightful and fun and easy, and you can play with that and enjoy it. And I thank you so much for watching these series, and I hope that they've been helpful to you as a teacher and as a student.